Hello friends, welcome to my channel. Today we are going to see crystal field splitting in octahedral, square planar and tetrahedral complex. Now we will see first octahedral. We know the structure of octahedral complex. There is a central metal ion surrounded by four ligands at four corners and two ligands upward and below the metal ion. This is a tetrahedral complex. Hmm. Now we know that in transition metals, the valence shell is d shell and it has 5 degenerate orbitals. That is like these are 5 degenerate orbitals, d orbitals. First is dxy, second dyz, third dxz, fourth dx square minus y square, and fifth dz square. Now we will see its arrangement. How the orbitals of what is the shape of the orbitals. First we will see dxy. This is x, y and z axis respectively. Now dxy, the orbitals of dxy are between the axis, that is x and y axis. This is xy. Between x and y axis there is dxy. Now we will see dyz. xyz. The dyz are between y axis and z axis. This is as below. This is dyz. Now we will see the shape of dxz. Where are they placed and its position, x, y and z. Now we will see dxz. It will be between x and z axis like this, and it will be like this. This is y axis, it will go. This is dxz orbital. Now we will see dx square minus y square. The dx square minus y square orbital is on the x and y axis. Dx and y square. It is like this. It is on the x and y axis. On x and y axis, which is different from these first three orbitals. Now we will see dz square, how it is arranged. X, Y, Z. Now this is dz square orbital has different arrangement. It is totally placed on z axis. This is like this. One lobe is here and one lobe is concentrated at the origin. This is dz square orbital. Now in octahedral complexes, the ligands approach the metal ion from the four corners, that is from all the on the through the axis of through x, y and z axis. Here this is z axis and this is x and y axis. The ligand approach from these positions. Now when the ligand approach from x, y and z axis, we know that dx square minus y square is present on the x and y axis, and therefore the ligand will interact more with these orbitals dx square and y square, and their energy will increase. Due to this increase in energy, there will and their energy will increase, and there will be great repulsion between the electrons of the metal and the ligand electrons. This will lead to the rise in the energy and greater repulsion, and therefore these orbitals will have higher energy. Also the dz square orbital is placed between the direction of uh, ligands, that is z axis. It is present on z axis and its energy will also increase due to the more repulsion between the electrons of the metal, valence electrons of the metal, and the negative charge on the, that is lone pairs on the ligands. Their energy will become higher. But in case of dx dy sorry dxy dyz and dxz orbitals, the lobes of these orbitals are between the axis. Between the axis means between x and y axis, like this. And so they will interact less with the ligand orbitals, and due to this there will be less repulsion between the uh, electrons of metals and that of ligands. And so the energy of these three orbitals will not increase, or will be less. So we can draw the splitting of these orbitals as, and this splitting due to the repulsion between the ligands and metal, electrons of metals and ligands, leads to the splitting of the d orbitals, which we call crystal field splitting. Now we will see how how what is the energy difference between them. These are the d orbitals of transition metal complexes: dxy, dyz, dxz, and dx square y minus y square and dz square. It will get excited due to the approach of ligands, and after the ligands bond with the metal ions, the energy of these orbitals, of these degenerate orbitals, will get splitted. This is dx square minus y square and dz square. Because the ligands, these orbitals are on the axis, their energy will be increased, and the orbitals which are between the axis, their energy will decrease. And these are dxy, dyz, and dxz orbitals. This is the barycenter. The energy of the dx square, and we call these orbitals, these two orbitals, as Eg, that is doubly degenerate, and this T2G, that is triply degenerate orbitals. Now the energy of the Eg orbitals will increase by 6 dq. Thus the splitting is denoted in dq, or del 0, that is octahedral splitting energy. This therefore the Eg orbitals will have energy plus 6 dq, will destabilize the compound by 6 dq of energy, and the T2G orbitals will stabilize the energy, stabilize the complex by 4 dq, or 0.4 del O, here 0.6 del O, and this difference is 10 dq, or 1 del O. So if there are suppose two electrons, if suppose there are three electrons in the T2G orbital, then it will stabilize the compound by -4, that is -12 dq. And if there is one electron in the Eg orbital, then it will destabilize the compound by 6 dq. So this was all about crystal field splitting in octahedral complexes. Now we will see crystal field splitting in square planar. We know the structure of square planar complexes ML4. They are ML4 type, that is 4 ligands. The two ligands on the z axis are removed, and that's why, as the two electrons which as the two ligands which are bonded at the z axis, that is axial position, are removed, the energy of the dz square orbitals get decreased, and it comes to lower energy state. and the energy as the ligands, as there are four ligands at the four corners, equatorial centers, the energy of the dx square and y square orbitals will remain the same, but the energy of the dz square orbital will go down. And also, as the ligands on the z axis are removed, the energy of dyz and dxz, which are along the z axis or between the x and z axis and y and z axis, will also decrease, and the energy of the dx square minus y square and dxy will increase due to the interaction between the ligands present on the x and y axis. Now we will see the crystal field splitting of square planar. This is the excited state, d orbital of the transition metal ion, and in square planar complexes this is dx square minus y square. The energy of the dz square orbital will get decreased. This is dz square. Also, the energy of the dyz and dxz will also decrease, and the energy of the, sorry, there is, we will see systematically. This is eg orbitals, and these are T2G, eg T2G. The energy of the dx square minus y square orbital will increase, and that of dz square orbital will decrease. Dxy will have more energy than dz square, and the dyz and dxz will have less energy. That is, it will stabilize the complex. Now here, if electron is present in dxy and dx square minus y square, it will destabilize the complex, and if the electrons are present dyz dxz, then it will stabilize the complex. This is the crystal field splitting in square planar. Now we will see crystal field splitting in tetragonal complexes. In tetragonal complexes, it is like distorted octahedral. This is a normal octahedral complex. Now we will see tetragonal. In tetragonal complexes, the ligands present at the axial position get far away from the metal ion, and due to this, the repulsion between the ligands and the metal electrons decreases to more decreases more, and thus this results in the decrease in the energy of the dz square orbitals. Now we will see their splitting. This is the excited. These are the degenerate d orbitals, that is T2G and Eg orbitals, thus Eg and T2G. Thus in tetragonal complexes, the dz square will energy will decrease, and that of dx square minus y square will increase. Sorry, and the energy of dxy will also increase, but to less in less proportion, and dyz and dxz will decrease. Now here we can see that the energy of dz square decreases and that of dxy increases, and also dyz and dxz decreases, but the energy of dxy is less than the dz square, as we have seen in square cranial complexes, in which the energy of the dz square is less than the dxy. This is because the ligands at the axial position, that is at z axis, are completely removed. But here in tetragonal complexes, the ligands are moved away from the metal but are not removed. That's why this energy difference is there. Now in the case of tetrahedral, now we will see tetrahedral complexes. First we will draw the diagram of tetrahedral complexes. 3D structure, what we call this 3D structure of tetrahedral complexes. We will draw a cube. At the center of cube there will be metal, and at the three opposite there will be tetrahedral orbitals. So we will denote it so that we can understand it more easily. This is the cuboid. Now this is the central metal ion at the center of the cube. These are the four ligands. At the edges of, at the vertex of four, at four vertices of the cube. Now here the ligands do not approach the metal cation through the direction of the axis. These are x, y, and z axis. They do not approach through this axis to the metal cation, but they approach between. That means as these bonds are not on the axis, it means that the ligands don't approach through the axis. That's why we know that dx square minus y square and dz square orbitals are present on the axis. Therefore, as the ligands don't approach to the axis, they will have less interaction with this. They will, that is, they will not overlap as in octahedral complexes with dx square minus y square and dz square orbitals. That's why their energy will decrease, and the orbitals which are present between the axes, that is dxy, dyz, and dxz, they will overlap more or interact more with the incoming ligands, as they are present between the axes, than the dx square minus y square and dz square orbitals, and this will lead to the increase in the energy of dxy, dyz, and dxz orbitals, and it will lead to decrease in the energy of dx square minus y square and dz square orbitals. Now we'll see the crystal field splitting in tetrahedral. It is inverse of that in octahedral complexes. This is the d orbitals degenerate. Now in this tetrahedral case, the T2G orbitals will have higher energy as they overlap more with the ligands, and thus it and in and the energy of the EG orbitals will decrease. Now in tetrahedral complexes, we call the degenerate orbital, that is three degenerate orbitals, as T2, and the two degenerate orbitals as E. The energy difference between these two states is 10 dq, or 1 del T. We call it crystal field stabilization energy, that is del T. This is the barycenter. Thus the electrons in T2 orbital will destabilize the complex by minus 4 dq or plus 4 dq, and the electrons in E orbitals will stabilize the complex by minus 6 dq. Thus it is the inverse of octahedral. Now we will compare the energy, that is the crystal field stabilization energy of tetrahedral and octahedral complexes. That is the energy of tetrahedral complexes, that is stabilization, that is 4 upon 9 that of octahedral. That is the octahedral, the crystal field splitting energy of octahedral complexes is 4 upon 9 times more than that of tetrahedral complexes. And this was all about the crystal field splitting in octahedral, tetrahedral, square planar and tetragonal complexes. So thank you. And if you like this video, please like it, share it and subscribe my channel, and please keep motivating me by giving me your important feedback so that I can improve myself. Thank you.